4.5 billion years ago, Earth was unrecognizable, a world of molten rock, toxic skies, and endless firestorms. In this journey, we'll explore what our planet was truly like in its first 2 hours of existence. If you enjoy ancient worlds, please like, subscribe, and share, and tell us in the comments, would you dare to visit the Hadean Earth? Thank you for watching. Now, let's begin. The story of the Hadean Earth begins long before any solid ground existed in a rotating cloud of gas and dust surrounding a young star. The sun, newly ignited, shines faintly compared to its future brightness, and its light filters through a vast nebula, rich in hydrogen, helium, and fine grains of heavier elements. Within this nebula, temperature varies sharply with distance from the central star. Near the sun, heat keeps most materials in vapor form, but farther out, dust begins to condense. Iron-nickel silicates and other refractory substances, the building blocks of rocky worlds, form solid particles that drift and collide. These grains move within a flattened disk drawn by gravity, yet influenced by rotation and turbulence. Over time, the countless encounters among particles lead to adhesion. Electrostatic forces first pull small grains together, then gravity takes over as clusters grow larger. A slow but relentless process begins turning clouds of dust into pebbles, pebbles into boulders, and boulders into planetary embryos. The region where Earth will form lies within the inner solar system, a zone of intense radiation and constant motion. Here, material is limited compared to the outer regions where giant planets take shape, but what remains is dense and metallic. The proto-Earth emerges not from a single creation event, but from millions of smaller collisions spread over millions of years. Each impact releases heat, melting local surfaces and welding bodies together. The growing mass begins to influence its surroundings, clearing a path through the disk, capturing smaller fragments and establishing a gravitational presence. In this early epoch, the solar system is crowded and chaotic. Countless bodies share overlapping orbits, and collisions are frequent. The newborn Earth remains only a fraction of its final size, its gravity still weak, but momentum builds as each encounter adds mass and energy. Heat from accretion rises within the forming sphere, and metallic components begin to separate from silicate ones. This marks the first step toward planetary differentiation, the process by which dense materials sink inward and lighter ones rise. In the surrounding space, the sun's radiation pushes lighter gases outward, leaving the inner planets deprived of hydrogen and helium. What remains are heavier elements forming compact rocky worlds. Dust continues to spiral inward toward the growing proto-Earth, feeding its surface with new layers of matter. Meanwhile, magnetic activity and solar wind shape the disk's evolution, sweeping away residual gas and altering orbital paths. Within tens of millions of years, the once transparent nebula thins and disperses, leaving behind a young sun encircled by the remnants of creation, planetesimals, fragments, and debris. The environment quiets compared to its earlier state, but the scars of formation remain visible in the craters and irregular shapes of surviving bodies. As the proto-Earth grows, the energy of impact increases exponentially. Each collision carries kinetic energy comparable to the gravitational potential of entire mountain ranges. When absorbed by the planet, that energy transforms into heat, raising internal temperatures high enough to melt vast portions of rock. The early surface alternates between molten and solid states, its appearance dictated by the frequency of impacts. With every new merger, the young planet's gravity strengthens, allowing it to hold more debris in orbit or draw it inward. Planetary embryos form nearby, some competing for material, others destined for catastrophic collisions. The path toward a stable Earth is defined by this interplay of accumulation and annihilation. the rotation inherited from the nebula, causes the planet to spin, gradually establishing a day-night rhythm. Though sunlight struggles to penetrate the thick haze of dust still present in the solar plane. Beyond Earth's orbit, Jupiter's immense gravity begins to stabilize part of the system, clearing space and influencing the trajectories of smaller bodies. Yet within the inner system, violence persists. Iron and silicate spheres continue to crash together, forming the terrestrial planets Mercury, Venus, Earth, and Mars. Around the forming Earth, the balance of forces becomes increasingly delicate. Collisions no longer merely add mass, they reshape the entire body. The largest impacts excavate enormous cavities, melt the crust, and throw vaporized rock into orbit. Through it all, gravitational attraction ensures that no fragment remains independent for long. The proto-Earth's composition becomes increasingly layered. Heavy elements like iron and nickel sink toward the center, while lighter silicates rise to form a primitive mantle. This differentiation produces a metallic core that begins to generate a magnetic field weak and unstable at first, but a vital feature in planetary evolution. The planet's surface remains a hostile ocean of molten material, continually replenished by infalling debris. Around it, smaller fragments form temporary satellites, only to spiral back and merge. The atmosphere, if any, is transient, composed of vaporized rock and gas released by impact, soon stripped away by solar wind. The system is one of constant exchange between matter and energy, between destruction and renewal. As the frequency of collisions gradually decreases, the proto-Earth stabilizes into a nearly spherical form. Its mass now exerts sufficient gravity to retain a portion of the gases released from molten rock. The surrounding region grows less crowded as remaining planetesimals are absorbed or scattered into distant orbits. By this stage, roughly a few tens of millions of years after the Sun's birth, the solar system begins to resemble its later architecture. Yet the Earth remains far from recognizable. Its surface is a restless expanse of molten rock. Its sky is darkened by dust. Its oceans and continents lie in the unimaginable future. Still, the essential structure is in place: a dense metallic heart, a silicate mantle, and the beginnings of a gravitational equilibrium. The transition from nebular dust to protoplanet marks one of the greatest transformations in natural history. In a span of cosmic brevity, what began as invisible motes orbiting a young star becomes a planetary body capable of storing heat, maintaining structure, and setting the stage for further change. As the nebular disk dissipates and the Earth's path clears, the first chapter of the Hadean world closes. From the quiet remnant of the solar cloud emerges a sphere of fire, solidifying in form but still fluid in fate. In the dim light of the early sun, the young Earth continues to grow within a sea of colliding worlds. Countless planetesimals, rocky and metallic fragments, ranging from meters to hundreds of kilometers in diameter, move through the inner solar system on unstable paths. Each orbit brings encounters, and each encounter carries the possibility of merger or destruction. The gravitational field of the proto-Earth strengthens with every addition of mass, drawing nearby bodies inward. When two collide, their motion converts to heat. Shock waves ripple through molten rock, vaporizing minerals and releasing plumes of gas into the tenuous space. This cycle of impact and recovery defines the Hadean stage of assembly. The process is relentless. Every few thousand years, a new body strikes, some glancing and some head-on. Smaller impacts melt the crust locally. Larger ones can liquefy vast regions or even reform the planet's outer layers entirely. For millions of years, the surface rarely cools for long. Vast impact basins fill with molten rock, cool briefly, and are obliterated by the next collision. Beneath this chaos, density separation continues. Iron and nickel sink deeper, forming a growing core, while silicates and lighter oxides move upward toward the surface. Gravitational energy released by this differentiation joins with the heat of impacts and the decay of short-lived radioactive isotopes to keep the entire body incandescent. In these conditions, solid crust cannot persist. Instead, transient rafts of partially solidified material drift atop molten seas, then sink again when the next surge of heat overwhelms them. The planet is in a continuous state of renewal. Around it, the remnants of the solar nebula linger as dust and gas. Solar wind, now stronger than before, begins to clear these remnants, thinning the disk and reducing the rate of incoming debris. Yet even as the environment empties, large bodies still cross the young planet's orbit. Their collisions dominate the planet's development, determining its final size, spin rate, and axial tilt. Some impacts deliver additional volatiles, water-bearing minerals, carbon compounds, and gases trapped in primitive asteroids. Others strip material away, sending molten fragments into orbit, or scattering them into space. The balance between gain and loss governs the pace of growth. With time, the Proto-Earth emerges as one of the few survivors among many competitors. Smaller protoplanets are either absorbed or ejected into distant orbits. In this competitive environment, gravitational interactions shape everything. A slight shift in trajectory can determine whether a body joins the Earth, collides catastrophically, or escapes forever. The young planet's path stabilizes gradually as neighboring zones are cleared. Angular momentum inherited from the nebula rotation continues to make the planet spin rapidly, perhaps completing a rotation in only a few hours. This rapid spin affects the planet's shape, causing an equatorial bulge and distributing molten material unevenly. The interior remains convective, with liquid silicates churning in immense cycles that transport heat outward. Above them, a transient crust forms and collapses in endless succession. The outer appearance is dominated by a reddish glow from molten rock and incandescent clouds. From space, the Proto-Earth would resemble a fiery sphere streaked with glowing fissures and encircled by a halo of vaporized minerals. Its atmosphere is thick with silicate vapor, sodium, and iron oxides, all driven upward by the heat of constant bombardment. Radiation from the sun ionizes these gases, creating faint auroral glows that shimmer over a surface perpetually in motion. During quieter intervals, droplets of condensed minerals fall like metallic rain, returning vapor to the molten surface. No stable air, no oceans, and no continents, yet exist only cycles of vaporization and condensation within a closed loop of extreme temperature. The young planet's density increases as heavy elements collect toward the core. This inward migration releases gravitational energy that adds to the heat budget sustaining the global melt for tens of millions of years. Eventually, a balance begins to emerge between the inflow of energy from impacts and the outward radiation of heat to space. As collisions become less frequent, temporary surfaces survive for longer intervals. Still, each stability is short-lived. A single large impact can reverse the trend entirely, plunging the planet once again into molten chaos. In this environment, the seeds of the Moon's formation are sown. Several planetary embryos continue to share similar orbits with Earth, and their gravitational influence leads to periodic close encounters. One of these bodies, roughly the size of Mars, follows a path that will eventually intersect Earth's, directly setting the stage for the event that will transform both worlds. Before that moment arrives, however, the Proto-Earth passes through a period of relative equilibrium. The last of the nebula gas has mostly dispersed, and sunlight begins to reach the planet unobstructed. The glow from the molten surface diminishes as heat loss outpaces input. Crystallization occurs in the uppermost layers, forming a thin crust of basaltic rock, fragile but continuous. The atmosphere, though dense, begins to change composition as silicate vapors condense and heavier gases settle. Carbon dioxide, nitrogen, and water vapor become dominant. These gases will form the foundation of later atmospheres, though they will be lost and renewed many times over before stability is achieved. The internal core, already rich in metal, begins to rotate independently from the mantle, hinting at the future dynamo that will one day produce a magnetic field strong enough to shield the surface from solar radiation. For now, solar wind strips away much of what the planet attempts to hold. Each new burst of volcanic activity replenishes what is lost, creating a constant exchange between the interior and the sky. The early atmosphere is not a shield, but a transient veil. As the planet continues to rotate rapidly, centrifugal forces and internal convection influence its internal structure. Mantle currents rise and sink, transporting molten material that carries with it both heat and chemical differences. Elements incompatible with solid phases accumulate near the surface, forming reservoirs that will later define the planet's geochemical complexity. Despite the violence of its surroundings, the Proto-Earth's evolution follows clear physical principles. The conversion of motion to heat, the segregation of matter by density, and the gradual reduction of energy through radiation. Over tens of millions of years, these processes transform a chaotic swarm of debris into a coherent planetary body. The atmosphere thickens and thins in cycles, the crust appears and disappears, and the planet's interior evolves toward a layered structure. What remains constant is the motion, the ceaseless transfer of energy and material that defines the Hadean epoch. By the time the Proto-Earth reaches nearly its full mass, the solar system has entered a quieter phase. The largest collisions have already determined the fates of the inner planets, yet one final encounter still awaits a collision that will exceed all others in scale and consequence. The Earth, though vast and molten, is not yet the planet that will sustain oceans or continents. It is a world of fire and metal awaiting its final transformation. The next impact will shape its destiny, giving birth to a companion that will govern its tides and stabilize its spin. The groundwork has been laid by countless collisions, but the story of accretion is not complete until the moon takes form from its aftermath. The Hadean Earth exists in a state of permanent transformation driven by the raw energy of collisions. Each impact delivers more than matter. It brings a surge of heat that reshapes the entire planet. The kinetic energy of incoming bodies travelling at tens of thousands of kilometers per hour converts instantly into shock and fire upon contact. Rock behaves like liquid under such force, vaporizing into glowing clouds that rise and settle again in seconds. The surface of the young Earth never rests. Craters form and vanish in molten seas. Mountains rise and collapse into magma plains. The scale of energy release defies ordinary comparison. A single large collision can release more energy than all volcanic activity in the planet's future history combined. During the height of accretion, such events occur frequently enough that the surface remains largely molten. The result is a world where solid and liquid are indistinguishable states where heat dominates every process. Deep within the planet, gravity compacts material under enormous pressure, adding another source of internal warmth. The heavier elements, iron, nickel, and cobalt, sink toward the center, releasing gravitational potential energy as they fall. The lighter silicates rise, forming a turbulent mantle that churns in convection cells hundreds of kilometers across. Radioactive isotopes, short-lived but abundant in the early solar system, decay within this fluid mass, adding further heat. Each of these processes impact compression, and radioactivity feeds the same cycle of melting and motion. Together they create a planet that glows from within, radiating energy, into space at a rate that exceeds any later epoch. The heat flux is so intense that even as the planet emits light like a dull ember, its surface cannot cool fast enough to solidify. Instead, the crust remains ephemeral, where a thin skin of rock forms convective currents from below crack it apart. Gases trapped in molten layers rise through fractures, releasing volatile compounds into the surrounding space. The atmosphere that forms is temporary and violent. It consists mainly of vaporized silicates, iron oxides, and sulfurous gases, all ionized by heat and sunlight. These gases scatter light in deep orange and red tones, giving the planet an eerie glow when viewed from space. Beyond the visible, infrared radiation carries away energy, the only effective means of cooling available. The sun itself contributes additional heat, though far less than what comes from within. The balance between incoming radiation and internal release defines the planet's thermal evolution. For millions of years, that balance favors the interior, preventing any stable crust from lasting more than a geological moment. Yet even in this inferno, the laws of thermodynamics ensure gradual change. Energy must disperse, and as impacts grow less frequent, the average temperature begins to decline. The cooling is uneven. Some regions struck repeatedly remain molten for longer, while others develop thicker layers of partially crystallized rock. The surface becomes a patchwork of glowing fields and darkened areas, constantly rearranged by convection and impact. Deep currents within the mantle circulate heat upward, feeding plumes that pierce the surface and renew the melt. This early convection sets the foundation for the later dynamics of the planet. The same processes that move molten rock will in distant ages move continents. At this stage, though, the entire mantle behaves as a single convective unit, with no stable lithosphere to separate it from the surface. The result is a global magma ocean, extending hundreds of kilometers deep. Within it, crystals form and dissolve continuously. Heavy minerals like olivine and pyroxene settle toward the base of the magma layer, while lighter ones remain suspended. This slow differentiation begins to structure the interior, creating chemical contrasts that will persist for billions of years. Above, volatile materials escape as the surface churns. Steam, carbon dioxide, and nitrogen accumulate only to be blown away again by solar wind or stripped by the energy of the next collision. The planet breathes in bursts of vapor and exhalations of fire. The constant release of energy drives a global circulation between the molten interior and the vacuum of space. Even the formation of the magnetic field, though still weak, is influenced by these energy flows. As the metallic core grows denser and hotter, its rotation relative to the mantle generates electrical currents. These currents give rise to a transient magnetosphere, too unstable to protect the surface, but strong enough to shape the paths of charged particles from the sun. The interaction of magnetic fields, plasma, and radiation creates a complex environment above the molten world. Particles spiral along field lines, forming auroral arcs that flicker faintly through clouds of vaporized rock. Far from this tumult, the outer solar system has already settled. The giant planets have formed, and their gravity stabilizes the orbits of remaining debris. Inside this gravitational architecture, Earth's fate remains bound to energy release. Each new collision injects heat faster than the planet can radiate it away, but the cumulative trend moves toward equilibrium. Over tens of millions of years, the number of catastrophic impacts declines. Smaller bodies dominate their arrivals, adding less energy than before. As a result, localized cooling becomes possible. The upper layers begin to crystallize faster than they are destroyed. The texture of the surface changes from a uniform molten expanse to a complex mixture of solidifying and remelting regions. The first long-lived crustal fragments may appear during this time, though none survive today. They float briefly atop the liquid mantle before being recycled into the deep interior. The rhythm of destruction slows and Earth enters a transitional phase. It is still a world of heat, yet now it contains within it gradient zones of higher and lower temperature regions where convection weakens and crystallization accelerates. These gradients mark the beginning of internal structure beyond simple layering. The energy budget that once overwhelmed the planet begins to reach balance. The interior remains molten, but the surface flickers between solid and liquid. Volatile elements released from degassing accumulate again, this time more persistently, because gravity has strengthened enough to retain them. A primitive atmosphere of steam and carbon dioxide thickens, creating a greenhouse layer that traps radiation and slows cooling further. This feedback keeps the surface warm even as impacts decline. The early planet thus becomes a self-regulating system balancing radiative loss against internal generation. The heat of collisions no longer dominates absolutely, but its legacy endures in the form of a core still liquid and convective. The energy of those ancient impacts sets the parameters for all that follows: the density of the interior, the chemistry of the mantle, the first volatile inventory, and the thermal inertia that will define Earth's evolution for billions of years. When viewed across time, the Hadean epoch is less an era of chaos than a process of organization through violence. Each collision, though catastrophic in isolation, contributes to equilibrium in the long term. The planet is forged not by serenity, but by the distribution of energy toward balance. As the final great impact approaches, the energy landscape has shifted from random bombardment to organized motion. The Earth stands poised at the threshold of the Moon's creation, its internal heat still immense, its surface still liquid, yet its future path already defined by the physics of the collisions that shaped it. The defining collision comes when the proto-Earth has reached nearly its full mass. In its path travels another large body roughly the size of Mars, composed of the same silicates and metals that built the inner planets. Its orbit shaped by gravitational interactions with the other protoplanets slowly drifts until the two bodies approach on a converging trajectory. Their closing speed exceeds 10 kilometers per second. When the smaller body strikes, the impact is oblique rather than head-on, releasing an energy so vast that it melts both worlds almost entirely. The force of the collision ejects a wide arc of molten rock and vaporized metal into orbit around the surviving Earth. For a moment, both planet and impactor are one incandescent mass distorted by gravity and rotation. Within hours, debris encircles the planet as a luminous ring. The remainder of the impactor merges with the Earth's core, deepening its metallic concentration and adding angular momentum. The young Earth now spins more rapidly than before, perhaps once every few hours, its equatorial region bulging outward from centrifugal force. The newly formed ring glows brighter than any later moon will ever shine, a band of molten droplets and silicate vapor orbiting within reach of the planet's gravity. Over time, fragments within this ring collide and coalesce, forming larger clumps that gather into a single sphere. This aggregation is governed by the same processes that built planets from dust, but now it occurs on a smaller scale and in orbit around Earth. Within a few decades to centuries, a new companion takes shape: the Moon. Its composition, dominated by silicates, depleted in volatile elements, reflects the high temperatures of its origin. Isotopic signatures preserved in lunar material billions of years later will reveal that it formed from the same source as the Earth, confirming that both bodies share a common ancestry. In the immediate aftermath, the Earth's surface is unrecognizable. The impact has erased any earlier crust, leaving a global ocean of molten rock thousands of kilometers deep. temperatures reach levels sufficient to vaporize silicate minerals entirely, creating an atmosphere composed of rock vapor steam and carbon dioxide. Pressure at the surface exceeds hundreds of atmospheres, and radiant heat from below keeps the air incandescent. Above this glowing planet, the nascent moon orbits much closer than it does today, perhaps only a few tens of thousands of kilometers away. Its tidal influence is immense, raising bulges in the molten surface that move rapidly around the equator. These tides, far stronger than any in the modern ocean, mix the upper layers of the magma ocean, distributing heat and delaying solidification. The gravitational relationship between Earth and Moon also begins to evolve immediately. As the Moon's orbit stabilizes, angular momentum transfers outward. The Earth's rotation slows gradually while the Moon recedes. This exchange of motion will continue across geological time, linking both bodies through tides that shape their mutual evolution. For now, though, the system is still in flux. The molten surface radiates energy into space, cooling first from the top. Crystals of olivine and pyroxene begin to form within the magma ocean, sinking toward the mantle as they grow. Lighter minerals float upward, accumulating near the surface. This differentiation establishes compositional layering that will persist into later eons. As the uppermost layer solidifies, it traps heat beneath, creating temporary stability before new convection breaks it apart. The process continues in cycles, gradually thickening the solid shell that will become the planet's first crust. Above the surface, the dense atmosphere remains opaque, scattering sunlight and trapping infrared radiation. The greenhouse effect keeps the planet's average temperature far above the boiling point of water, preventing condensation. Clouds of silicate droplets drift through the air like metallic mist. When these droplets fall, they evaporate before reaching the surface, feeding an endless rain of vapor. Only after millions of years of cooling will the atmosphere clear enough for the first true light of the sun to touch solid rock. The Moon, meanwhile, continues to evolve. Initially molten from the energy of its own formation, it too develops a magma ocean. As this lunar ocean crystallizes, lighter minerals float to the top, forming a bright crust of plagioclase feldspar. These anorthositic highlands reflect sunlight, making the young Moon a brilliant object in the Earth's perpetual twilight. Its proximity causes dramatic tidal heating within its interior, keeping it active for longer than would otherwise be possible. Debris from smaller collisions still falls upon both bodies, adding craters that will never fully fade. The shared environment of Earth and Moon becomes a dynamic laboratory of heat exchange, tidal motion, and orbital evolution. On Earth, tidal forces continually reshape the molten surface, driving currents within the magma and stirring the deep mantle. This mixing influences how the planet differentiates, how metals concentrate in the core, and how gases escape to form the atmosphere. As cooling proceeds, volcanic plumes puncture the solidifying crust, releasing volatiles trapped within. Steam, carbon dioxide, sulfur dioxide, and nitrogen accumulate above the surface, building an atmosphere thicker than that of Venus today. For a time, the entire planet is enveloped in clouds so dense that no starlight penetrates. Only the faint red glow of the molten ground filters upward, illuminating the lower atmosphere in shades of copper and gold. From the Moon's surface, Earth appears enormous, its disk filling much of the sky, glowing red at the edges, streaked with storms of molten vapor. The two worlds exchange energy through radiation tides and impacts from the remaining debris of the early solar system. Gradually, the rate of impacts declines. The orbits of major bodies stabilize and the region near Earth clears of large projectiles. The young planet enters a quieter stage of evolution, though its surface remains far from solid. The magma ocean still churns, but heat loss to space is now faster than the supply from residual impacts and radioactivity. Within several tens of millions of years, the upper mantle begins to crystallize extensively. Solidification proceeds inward from the surface and outward from the core, releasing latent heat and forming a boundary between solid and liquid layers. These boundaries will later control mantle convection and plate formation, but in the Hadean they remain unstable and fluid. Eventually, as the crust thickens, the planet's albedo increases, reflecting more sunlight and accelerating cooling. The dense atmosphere begins to condense, and water vapor collects as rain for the first time, though it cannot yet persist on the searing surface. The impact that once destroyed everything now enables the possibility of stability. The formation of the moon stabilizes Earth's axial tilt, preventing chaotic variations in climate that would otherwise occur. This subtle effect will prove crucial in the planet's long-term evolution, but in the Hadean Age its significance is only potential. What remains visible is the slow transition from a molten sphere to a planet with structure, a core, a mantle, and a crust in the making. The catastrophic impact has both erased and defined the planet, providing not only its companion, but also the conditions that will one day allow oceans, continents, and life. The world that emerges from this event is still young, still glowing, but it now moves within a more stable orbit under the steady pull of its satellite. The violence that shaped it begins to subside, replaced by the quiet work of cooling and crystallization. From this calm, the earlier solid surfaces will arise. After the moon-forming impact, the entire surface of the young Earth is molten. A global magma ocean extends from pole to pole, a restless sea of silicate melt hundreds of kilometers deep. The heat of formation combined with the radioactive decay and the lingering energy of impact keeps temperatures so high that no solid crust can persist. From orbit, the planet glows a deep orange red, its surface rippling like liquid metal beneath dense clouds of vaporized rock. The air itself is opaque, composed of steam carbon dioxide, sodium, and silicate dust that scatters the faint light of the distant sun. Radiation escapes slowly through this thick shroud, and cooling becomes an arduous, uneven process. Yet cooling must happen, and it begins at the surface where heat radiates into space most efficiently. Tiny crystals form first at the upper boundary between liquid and gas, where temperature falls below the freezing point of silicate minerals. These crystals, mainly olivine and pyroxene, drift downward into the molten mass, adding density variations that stir convection currents. The entire ocean circulates like a planetary cauldron, driven by buoyant plumes rising from deep within and descending sheets of crystallized material falling from above. This convective churning defines the internal dynamics of the early mantle. The process is not uniform. Some regions cool faster, forming thicker crystallized layers that resist motion, while others remain fluid, heated by the continued release of latent energy from the deep interior. The planet's rotation introduces further complexity, causing convective cells to spiral and align along the equator. The combination of thermal and rotational forces turns the magma ocean into a dynamic system, where material is continually exchanged between surface and depth. Over time, chemical differentiation begins. The heavy elements sink, lighter ones rise. Iron-rich minerals move toward the mantle base, while lighter silicates and incompatible elements concentrate near the surface. These compositional gradients will define the chemical identity of the Earth's mantle for the rest of its history. The young moon orbiting nearby exerts powerful tidal forces on the molten planet. Its gravitational pull raises massive bulges that migrate around the globe, causing additional mixing and frictional heating. Each rotation of the planet still lasting only a few hours, moves these tidal bulges through the magma, dissipating energy and delaying cooling. Yet despite this resistance, the system slowly evolves towards solidification. As the surface cools, gases trapped within the melt escape in immense volcanic plumes. Steam, carbon dioxide and sulfur compounds pour into the atmosphere, increasing its density and creating a greenhouse effect that maintains high surface temperatures even as radiative loss intensifies. The sky glows with scattered light from incandescent clouds. Occasionally, silicate droplets condense and fall like molten rain, evaporating before they reach the magma below. From above, the planet appears alive, its surface in perpetual motion, its atmosphere churning with heat and dust. In the deeper regions, pressure increases to levels that alter the behavior of silicate liquids. The lower mantle begins to crystallize earlier than the upper layers, forming minerals stable only under immense compression. These dense crystals settle into a growing basal layer that will later serve as the foundation for long-term mantle convection. The crystallization process releases additional heat, which slows cooling and creates thermal gradients that drive new convective patterns. The early Earth thus becomes a self-organizing system, balancing heat production, radiation, and chemical segregation in continuous feedback. Over millions of years, as the magma ocean gradually thickens with solid material, the first persistent crust begins to appear. This crust is not yet continental or even stable. It forms as a thin layer of basaltic rock floating atop the molten mantle, repeatedly broken and recycled by upwelling currents. In some regions, it survives long enough to develop rough textures and ridges before being swallowed again. The cycle of creation and destruction is relentless but essential. Each iteration extracts more heat from the interior, allowing the surface to stabilize for longer intervals. The atmosphere evolves alongside the solidifying crust. The early silicate vapor cools and condenses, leaving behind gases dominated by steam and carbon dioxide. As water vapor thickens, the greenhouse effect intensifies, maintaining surface temperatures above the melting point of rock, despite the declining energy from impacts. Eventually, as radiative cooling surpasses internal heat flow, temperatures begin to drop below critical thresholds. The magma ocean contracts and convection slows. Crystallization accelerates in the uppermost layers, forming an increasingly rigid shell. Beneath this shell, molten regions persist for tens of millions of years, their slow movement continuing to shape the planet's surface from below. The residual heat trapped within ensures that volcanism remains vigorous, with enormous plumes piercing the crust and spreading pools of lava across newly solidified areas. These events create transient land masses that resemble islands of glass floating on a sea of fire. Each eruption releases more volatile elements, gradually enriching the atmosphere and setting the stage for the future hydrosphere. Meanwhile, the Moon continues to retreat its orbit, expanding as Earth's rotation slows through tidal friction. The gravitational interaction between the two bodies decreases, reducing the tidal stirring of the magma ocean and allowing the surface to cool more efficiently. This change marks a turning point. The molten planet begins its transition toward a solid exterior. In the cooling atmosphere, silicate dust aggregates and falls as ash-like particles, blanketing parts of the crust in mineral residue. Beneath, chemical reactions between solidifying minerals and trapped volatiles form early reservoirs of gases that will later feed volcanic systems. The balance between degassing and condensation determines the evolving pressure and composition of the air. Eventually, as temperatures fall below roughly 2000 degrees Celsius, silicate rain ceases, and the atmosphere becomes dominated by dense steam clouds. Lightning flashes within these clouds, discharging the energy of a still volatile environment. The Earth's appearance changes from a glowing orb to a dim red sphere beneath a thick grey envelope. Cooling accelerates as radiation escapes through gaps in the cloud cover, and the first patches of solid surface survive for extended periods. These early crustal areas, though temporary, mark the transition from a wholly molten world to one capable of sustaining persistent land. Still beneath their fragile veneer, the mantle remains molten, convecting slowly, and maintaining internal temperatures high enough to erase any structure that endures too long. The global magma ocean does not vanish all at once. It retreats layer by layer, crystallizing from the bottom upward and the top downward until only isolated reservoirs remain. In these deep pockets, heat will persist for hundreds of millions of years, feeding the volcanic and tectonic activity that defines the planet's later evolution. The completion of this transition marks the end of the Earth's purely molten stage and the beginning of its geologic history. The surface, though scarred and unstable, is now a place where solid matter can exist, where heat and gravity have achieved a fragile balance, and where the groundwork has been laid for everything that will follow: the crust, the oceans, and eventually the conditions that make the planet habitable. As the molten surface of the Hadean Earth begins to cool, the relentless brightness that once defined the planet fades. The magma ocean, still immense, now bears a thin, darkened skin. This primitive crust forms where surface temperatures drop below the melting point of silicate rock. It is fragile and temporary, a crust in constant tension between solidification and destruction. Convective plumes from the mantle rise with tremendous force, breaking through the surface and flooding entire regions with lava. Yet each episode of renewal carries the planet closer to stability. The formation of this first crust marks a significant transition. The Earth's exterior shifts from a wholly liquid state to a solid one that can momentarily endure. The earliest crust likely consists of basaltic rock, dense and fine-grained, born from rapidly cooled lava. Its texture is smooth at formation, but soon fractured by thermal contraction. Cracks radiate outward from cooling centers, allowing gas and magma to escape through fissures. Steam carbon dioxide and sulfur dioxide pour into the thick atmosphere, maintaining a blanket of heat that slows further cooling. Even as the planet loses energy to space, the greenhouse effect from this dense gas mixture traps much of it, creating a feedback that delays the final solidification of the crust. Still cooling continues, driven by radiation through the upper atmosphere and by convection beneath. The surface alternates between fiery oceans and solidified fields, with the ratio of solid to liquid increasing gradually over time. Each surviving fragment of crust floats upon the molten mantle, like an island adrift on a sea of heat. These islands merge, sink, and reform in endless cycles. In some places, the crust thickens as new layers of solid rock accumulate atop older ones. In others, impacts from remaining debris in the solar system shatter the surface, excavating molten basins that glow brighter than the surrounding terrain. The period of heavy bombardment has not yet fully waned, and the Earth's face remains in flux. Yet in the intervals between impacts, the crust grows more resilient. Cooling from below stiffens it. Contraction from above fractures it into plates of varying size. Beneath these plates, convection cells within the mantle continue to transport heat outward. The difference in density between solid crust and molten mantle allows the crust to float, a process that marks the beginning of isostatic balance, the same principle that will later govern the movement of continents. The earliest crust, however, is thin and dense, composed mostly of mafic minerals rich in iron and magnesium. It differs fundamentally from the lighter continental crust that will emerge billions of years later. Its lifespan is short because it lacks the buoyancy to resist recycling. When heat accumulates below the crust, founders and sinks back into the magma, releasing trapped gases and heat in a self-regulating cycle. Over time, this process begins to extract heat more efficiently from the interior, encouraging further solidification. As molten regions become smaller, they form localized volcanic centers surrounded by cooler plains. These plains, though transient, represent the first relatively stable surfaces on Earth. The planet's color changes from red-orange to dark grey as cooling silicates solidify. Above, the atmosphere remains thick with steam and volcanic gases glowing dimly under a sun still partially veiled by dust. The first lightning storms rage through the upper atmosphere, driven by convection between hot and cool layers. Electrical discharges flash across the sky, illuminating the turbulent clouds that swirl over a landscape of rock and fire. Beneath this chaotic atmosphere, the solid crust grows thicker in places where cooling is most efficient, particularly near the poles and in regions less disturbed by tidal stress from the nearby moon. The moon, now farther away, continues to exert a gravitational pull that shapes Earth's tides and subtly influences its rotation. Each tidal flexing releases energy as heat, but the magnitude diminishes with distance, allowing the crust to endure longer without complete melting. Slowly, the surface stabilizes into a pattern of solid regions separated by narrow belts of molten rock. These boundaries mark the earliest prototectonic features zones, where thermal stress and internal motion concentrate deformation. Although true plate tectonics does not yet exist, the physical groundwork is present: rigid plates above, convecting mantle below. The crust, though unstable, insulates the interior, reducing the rate of heat loss and creating gradients that drive long-term evolution. The first crustal rocks undergo chemical alteration as they interact with gases from the atmosphere and with condensates forming from volcanic vapors. Minerals such as feldspar and pyroxene weather, superficially forming primitive clays and oxides that coat their surfaces. These reactions begin the slow chemical cycling between rock atmosphere and water that will dominate Earth's later history. Though liquid water cannot yet persist on the surface, traces of interaction between hot rock and atmospheric moisture already shape the chemistry of the crust. The atmosphere itself begins to change in composition. As silicate vapor condenses and falls out, the remaining gases become dominated by steam and carbon dioxide. Water vapor, no longer constantly replenished by rock evaporation, starts to accumulate in the lower atmosphere. When surface temperatures eventually fall below the critical point of water, condensation becomes possible. Clouds thicken and rain begins to fall intermittently, though most droplets evaporate before reaching the ground. Over millions of years, however, these cycles of precipitation and evaporation intensify. The constant rainfall erodes the crust, chemically transporting dissolved minerals back into the molten regions and influencing the planet's evolving geochemistry. Meanwhile, volcanic outgassing continues unabated, releasing new gases that replenish the atmosphere and maintain high pressure. This interplay between cooling crust and degassing mantle defines the planet's next stage. The balance between heat retention and radiative loss determines whether the crust can persist long enough for oceans to form. Eventually, the declining rate of bombardment and the continued retreat of the moon reduce the energy input from external and tidal sources. Cooling accelerates. The molten reservoirs contract, becoming localized beneath thicker crustal areas, and the planet's surface grows darker and more stable. The early crust now acts as both shield and conduit, shielding the mantle from space and channeling its remaining heat through volcanic systems. In this balance, the first sustained land masses appear, though they remain fragile and subject to renewal. Their formation marks the end of the Earth's fully molten epoch, and the beginning of an era in which solid rock dominates the surface. With this transition, the stage is set for the condensation of the hydrosphere. The air, still thick and hot, holds immense amounts of water vapour waiting to descend. The first crust, though thin and unstable, provides the foundation upon which oceans will one day gather and persist. The molten world has given way to a solid shell capable of bearing the weight of water and atmosphere alike. As the first crust stabilizes across portions of the Hadean Earth, gases trapped in molten rock begin to escape through fractures and volcanic vents, forming the planet's earliest true atmosphere. This degassing process transforms the composition of the air from one dominated by transient silicate vapor to one rich in volatile compounds. Steam, carbon dioxide, nitrogen, sulfur dioxide, hydrogen, and trace amounts of methane and ammonia pour from the surface in immense plumes. Each eruption releases both heat and gas, adding to the dense envelope that now blankets the cooling world. The air grows heavy and opaque, its pressure measured in hundreds of times that of modern Earth's sea level. Temperatures remain far above the boiling point of water, preventing any precipitation from reaching the ground. Instead, clouds of steam swirl endlessly through the dense atmosphere, condensing and evaporating in cycles that redistribute heat and moisture across the surface. Beneath this thick veil, the crust continues to fracture and reform its dark basaltic plains, glowing at the edges where lava seeps upward from the mantle. Volcanic activity is ubiquitous, with towering fountains of molten rock rising kilometers into the sky. These eruptions are not localized as they are today, but widespread, fed by a mantle still in motion from residual heat. Through this constant exchange between the interior and the surface, the planet's volatile inventory is transferred from rock to air. Much of the atmosphere's mass originates within the planet itself, rather than from external sources like comets or asteroids. The gases released carry with them the chemical fingerprint of the early mantle, establishing the baseline composition for Earth's future evolution. Water vapour is the most abundant constituent, followed by carbon dioxide. Together they form a greenhouse blanket that traps infrared radiation and keeps surface temperatures high enough to maintain widespread volcanism. Nitrogen, less reactive and heavier, accumulates over time as other gases condense or are absorbed into rock. The result is an atmosphere dense, dynamic and chemically active. Lightning, driven by convection and dust friction, ignites across the turbulent skies. Electrical discharges split molecules, forming radicals that react with one another to produce new compounds. The air is a laboratory of high-energy chemistry, though far too hot to allow complex molecules to persist for long. The continual input of gases from volcanic degassing replenishes the atmosphere faster than sunlight or chemical reactions can alter it. The balance between addition and loss remains dynamic, but the overall trend is toward accumulation. The earliest magnetic field, weak but present, begins to offer some protection against solar wind, reducing atmospheric stripping. Still, particles from the sun interact with the upper atmosphere, creating auroras that ripple faintly through the thick haze. These processes mark the beginning of atmospheric stability, though stability in this era means only persistence rather than equilibrium. The composition fluctuates with each volcanic episode. As gases cool and react, some condense into droplets of liquid or solid aerosols that fall back to the surface, contributing to the chemical evolution of the crust. Sulfur compounds in particular play a major role, forming dense clouds of sulfuric droplets that absorb sunlight and influence the planet's thermal balance. Periods of cooling alternate with renewed heating as volcanic outbursts release fresh material. The result is a slow oscillation of temperature and pressure, a breathing pattern that spans millions of years. Over time, the intensity of volcanism begins to decline, though it remains globally significant. The mantle cools and becomes more viscous, reducing the rate at which gases escape. This shift marks a gradual change in the atmosphere's evolution. With fewer fresh emissions, the chemical interactions among existing gases grow more influential. Carbon dioxide reacts with silicate minerals in the crust, forming carbonates that trap carbon within rock. Water vapor continues to dominate, but as surface temperatures drop closer to the critical point of water, condensation becomes increasingly likely. Thick clouds form continuously, their bases lowering as the air cools. Each new layer of cloud increases albedo, reflecting sunlight and promoting further cooling. Eventually, the greenhouse feedback that once kept the planet molten begins to weaken. The Earth approaches a threshold at which steam can condense into liquid water. Before that transition, the atmosphere reaches its maximum density. Pressure at the surface may exceed 100 bars, enough to compress the air into a supercritical fluid near the ground. In this environment, chemical weathering begins. Volcanic gases react with the surface, forming layers of altered basalt rich in hydrated minerals. These reactions draw water and carbon dioxide from the air, linking the atmosphere and crust in a continuous cycle. The first signs of long-term geochemical regulation appear here as the surface absorbs some of the volatiles that once escaped from within. Above, the clouds thicken further, creating a uniform grey canopy that scatters the dim light of the young sun. The planet's days and nights blur together under the constant glow of diffused radiation. From space, the Earth appears featureless, its surface hidden beneath a global layer of mist. Only the faint outlines of active volcanoes are visible through the cloud tops, their plumes reaching high into the stratosphere before dissipating. The sound of the planet, if it could be heard, would be one of perpetual thunder, boiling vapors, crashing waves of heat, and the ceaseless hiss of volcanic degassing. Gradually, as internal heat flow decreases and the rate of impact continues to decline, the atmosphere begins to cool enough for new processes to dominate. The upper layers of the air start to condense water droplets that persist for longer before evaporating. These droplets coalesce into larger drops, falling as rain. The first precipitation evaporates before touching the ground, but with each passing millennium the lower atmosphere cools further. Eventually, rain reaches the surface, forming transient pools that boil away only to condense again. The hydrological cycle begins, though it is still unstable and brief. Each cycle extracts heat from the surface, hastening the planet's cooling and thickening the crust. The interaction between rain and rock produces chemical weathering that leaches elements like sodium, potassium, and calcium into runoff, setting the stage for the composition of future oceans. Through this gradual interplay, the primitive atmosphere evolves from a product of violent degassing to a stable system capable of sustaining water in liquid form. The transition is neither sudden nor uniform, unfolding over tens of millions of years as the planet balances energy and chemistry. By the end of this stage, Earth is no longer a world of constant eruption and evaporation, but a planet enveloped in dense steam clouds above a surface that occasionally glimpses stability. The crust beneath has thickened, the mantle has cooled, and the air, once a furnace of rock vapor, now carries the ingredients that will soon condense into the first oceans. When the Earth's surface finally cools below the critical point of water, a profound transformation begins. The steam that once filled the air starts to condense into rain that can reach the ground without instantly evaporating. What had been an atmosphere of vapor becomes a system of clouds, storms, and precipitation. The Hadean sky darkens as moisture condenses into dense masses of cloud that span the planet. Lightning flashes through their depths, illuminating a landscape of black rock and glowing lava. Rain falls in unending torrents, covering the surface with sheets of water, that hiss and boil as they meet hot ground. The first true hydrosphere forms in this continuous cycle of rainfall, evaporation, and condensation. The process is violent at first. Each drop of rain evaporates on contact, extracting heat and thickening the clouds above. Steam rises in plumes, feeding new storms that move across the planet in waves. Over millions of years, as surface temperatures continue to decline, the balance shifts. Rain begins to pool in low areas, forming temporary lakes, and spreading into basins created by cooling and contraction of the crust. These basins grow as volcanic activity subsides and impact frequency decreases. Eventually, they merge into larger bodies of water, the first transient oceans. The atmosphere, now heavily laden with carbon dioxide and nitrogen, traps heat efficiently, but no longer prevents condensation. The result is a warm, humid planet wrapped in constant mist. The oceans that form under these conditions are not yet blue or clear. They are dense with dissolved minerals, metals, and silicates, leached from freshly solidified rock. Their colour is dark and reflective, their surface often broken by eruptions and falling debris. Chemical reactions between seawater and the crust begin immediately, altering both. The newly formed crust interacts with water through hydrothermal circulation, where hot fluids penetrate fractures and react with minerals. This process leaches elements from the rock, enriching the oceans with ions that will become the foundation of future chemistry. As the hydrosphere stabilizes, these reactions regulate surface temperature, removing carbon dioxide from the air and storing it as carbonate minerals. The early oceans become a vast heat sink, moderating temperature extremes across the planet. The cycle of evaporation and rainfall redistributes energy and begins to shape the global climate. The moon, already receding but still much closer than today, exerts strong tidal forces on these new seas. Tides sweep across the molten crust, carving shallow basins and amplifying mixing between water and rock. This mechanical energy enhances weathering and accelerates the formation of secondary minerals. Even as the surface grows cooler, volcanic activity remains widespread. Vast fissures release heat and gas from the mantle, creating submarine lava flows that solidify on contact with water. Steam vents and geysers erupt along fractures, producing clouds of vapors that mix with the dense air. Around these hydrothermal systems, water circulates through newly formed crust, cooling the interior and transferring minerals to the surface. This interaction between liquid water and volcanic heat defines much of the Hadean environment. The oceans act as both stabilizer and catalyst, cooling the surface while driving chemical exchanges. The balance between ocean formation and atmospheric renewal becomes the dominant feedback system of the planet. The hydrosphere grows as volcanic degassing continues to supply water vapor that condenses and accumulates. Cometary impacts, though less frequent than before, may also deliver additional water, enriching the total volume of the early oceans. The combined contribution from degassing and external delivery creates a planet where liquid water covers much of the surface. Over time, evaporation and rainfall establish global circulation patterns. Warm air rises above volcanic regions, carrying moisture high into the atmosphere. It cools, condenses, and falls again, creating powerful storms that move heat toward the poles. These cycles erode rock, transport sediments, and sculpt the early landscape into plains, ridges, and depressions. Each drop of rain, each wave, and each eruption contributes to the reshaping of the young crust. The sound of the planet changes from the roar of constant eruption to the rhythm of rainfall and thunder. The first oceans are shallow and unstable, frequently boiled by impacts or by the intrusion of a magma from below. Yet their persistence increases as the planet's interior continues to lose heat. With each passing million years, the temperature gradient between surface and interior grows steeper, allowing the outer layers to remain solid, while the deep mantle convects slowly. This separation marks the beginning of thermal stratification, a critical step in stabilizing the hydrosphere. The atmosphere evolves alongside. As water condenses, atmospheric pressure drops, slightly reducing the greenhouse effect and promoting further cooling. Carbon dioxide dissolves into the oceans, forming carbonic acid that reacts with basaltic rock. These reactions gradually draw carbon from the air into solid minerals, shifting the chemical balance toward nitrogen-dominated conditions. The dense steam clouds thin, revealing a dim sun through breaks in the overcast sky. For the first time, light reaches the surface in sustained intervals. The interplay of light, heat, and water creates new patterns of energy flow, setting the stage for future climate regulation. Despite the progress towards stability, the surface remains hazardous. Meteorite impacts still occur, though less frequently, and each large strike can momentarily vaporize sections of ocean, throwing steam and rock into the atmosphere. Yet even these cataclysms cannot completely remove the hydrosphere. The oceans reform quickly replenished by continuous condensation. Their persistence becomes one of the defining features of the planet. Chemical evidence preserved in the oldest known zircon crystals, tiny minerals later found in much younger rocks, suggest that liquid water existed on Earth more than 4 billion years ago. These minute remnants confirm that the hydrosphere stabilized early and endured through cycles of bombardment and renewal. Beneath the surface, hydrothermal systems become widespread. Seawater seeps into fractures, reacts with hot rock, and emerges enriched in metals and silicates. The resulting plumes mix with ocean water, creating gradients of temperature and chemistry that persist for millennia. In this interplay between hot interior and cool surface energy flows outward in a controlled manner. The planet that once radiated heat chaotically now dissipates it through structured systems, volcanism, ocean circulation, and atmospheric convection. The hydrosphere's creation transforms not only the surface, but also the deep interior. As oceans form, they exert pressure on the crust, influencing the behavior of mantle convection and the formation of new rock. Water penetrates downward, altering the melting point of minerals and promoting localized melting that feeds volcanic activity. The presence of water changes the mechanics of the planet itself, lubricating motion at boundaries between solid and molten regions. Over millions of years, these effects begin to shape the patterns of future tectonics. The formation of the hydrosphere marks the end of Earth's transformation from a world of fire to one of water. The surface, once molten, is now sculpted by rainfall waves and tides. The air, once thick with silicate vapor, is now dominated by steam and gases more familiar to the modern atmosphere. Though still hot and dense, the planet now supports liquid water over large areas. The stage is set for chemical cycles to stabilize, for erosion to sculpt the crust, and for the interplay of rock, air, and ocean to define the next steps of the Earth's long evolution. Even as oceans spread and the first crust thickens, the Hadean Earth remains under siege from space. Countless fragments left from planetary formation continue to cross its orbit. Some are small, burning harmlessly upon entry, but others are vast asteroids tens or hundreds of kilometers wide that can reshape the planet's surface in an instant. This prolonged era, known as the Late Heavy Bombardment, marks one of the most violent intervals in Earth's early history. Over tens of millions of years, the planet experiences repeated impacts powerful enough to melt vast regions of crust and vaporize oceans entirely. Each collision releases energy on a scale beyond any later volcanic or tectonic event, temporarily restoring the surface to molten conditions. The hydrosphere that had so recently formed evaporates again and again, only to condense after the atmosphere cools. This cyclic destruction and renewal defines the Hadean surface. It is not a stable world, but one in constant recovery. The impactors originate mainly from the outer solar system, destabilized by gravitational interactions among the giant planets. They arrive at high velocity, carrying not only kinetic energy, but also volatile materials. Some deliver water and carbon compounds, while others strip away portions of the atmosphere. The net effect is complex impacts destroy surface features, yet contribute to chemical enrichment. Each crater excavates the crust and exposes the mantle below, allowing gases to escape and minerals to exchange. The energy of impact melts rock locally, forming vast pools of magma that cool into new crustal layers. Over time, these layers overlap and merge, building a geological palimpsest where no feature lasts unaltered. Between major impacts, quieter periods allow cooling, condensation, and partial stabilization. Oceans return, filling basins formed by earlier collisions. Rainfall continues to leach minerals from exposed rock, altering the chemistry of both crust and sea. Hydrothermal systems thrive near impact sites where heat from melted rock drives circulation of water through fractured crust. These regions become zones of intense chemical activity rich in dissolved metals and gases. The constant alternation between destruction and recovery turns the Earth into a dynamic laboratory of energy exchange. The frequency of impacts gradually declines as the solar system clears of debris, yet during the height of bombardment the scale of events is staggering. Some impactors excavate basins hundreds of kilometers wide, throwing ejecta across hemispheres. Shock waves travel through the mantle, triggering volcanism on a global scale. The combination of impact heating and volcanic outgassing thickens the atmosphere, saturating it again with steam and carbon dioxide. For long intervals, sunlight fails to reach the surface, blocked by clouds of ash and vaporized rock. The surface remains in twilight, illuminated only by the dull glow of molten fields. Cooling proceeds slowly under these conditions, and when it does, new crust forms over regions still fluid beneath. This layered structure introduces heterogeneity into the early lithosphere zones of differing composition and temperature that will influence later tectonic behavior. The atmosphere, meanwhile, undergoes continuous regeneration. Each impact strips away portions of the upper layers, but also releases new gases from beneath. Over time, this exchange balances loss and supply. Nitrogen resistant to chemical reaction becomes increasingly dominant as carbon dioxide and water vapor condense, or are sequestered into minerals. The overall pressure remains high, and the greenhouse effect continues to regulate surface temperature within a range that allows water to return between impacts. In this uneasy equilibrium, the hydrosphere persists, though always at risk of vaporization. Evidence for these cycles survives indirectly in the isotopic composition of ancient minerals preserved within much younger rocks. The ratios of oxygen isotopes in certain Hadean zircons suggest repeated interactions between hot rock and liquid water, implying that even amid bombardment, surface water repeatedly reappeared. This resilience of the hydrosphere underscores the planet's capacity for self-restoration. No impact, however immense, could permanently undo the processes that maintained water on the surface. Between bombardments, erosion and sedimentation reshape the crust. Rain and runoff carve channels through cooling lava, depositing mineral grains in low areas. These sediments are quickly buried or remelted, yet their formation indicates a surface capable of cycling material. Volcanism remains intense, fed by residual heat from both the mantle and impacts. Vast lava plains cover the land, solidifying into dark basaltic expanses, Over these rain falls again, forming transient lakes that steam under the heavy atmosphere. The hydrologic and volcanic cycles interact, transferring heat and chemicals between Earth's layers in a feedback loop that moderates temperature and composition. As time advances, the bombardment wanes. The largest impacts become rare, and the intervals between them lengthen. The crust, though scarred, grows thicker and more resistant. The magma ocean has long disappeared, replaced by localized melt zones that act as reservoirs for volcanic activity. The surface is no longer globally molten, but rather a mosaic of solid regions separated by zones of instability. Oceans, though often disturbed, remain extensive. Their chemistry evolves as interactions with basalt draw down carbon dioxide and supply ions like calcium, magnesium, and sodium. These reactions begin to buffer the planet's atmosphere, laying the groundwork for long-term climate stability. Even so, the energy of impacts leaves enduring effects. Shock metamorphism alters minerals, producing high-pressure forms that will persist in the geological record. The deep crust bears traces of repeated melting and recrystallization, recording the relentless reworking of early Earth. The global pattern of heat flow changes as bombardment declines, shifting from external to internal sources. The mantle's convection becomes the primary driver of surface renewal. Volcanic outgassing continues, but at reduced intensity, and the balance between release and sequestration of gases begins to stabilize. The air grows clearer as particulate matter settles, allowing more sunlight to reach the surface. With increased light, temperature gradients strengthen between day and night, giving rise to atmospheric circulation patterns more complex than before. Winds distribute moisture and ash across the globe, further eroding highlands and smoothing the terrain. The appearance of the planet transforms once again from a world dominated by impacts to one shaped by weather and internal motion. The moon, still massive in the sky, exerts constant tidal influence, slowing Earth's rotation and lengthening days. Each tidal cycle transfers angular momentum, causing the moon to drift outward slowly. The weakening of tidal forces reduces crustal stress, allowing thicker plates to form without immediate destruction. These evolving conditions mark the end of the most catastrophic phase of bombardment. The Earth, though still restless, now holds features that endure beyond individual events. Oceans persist, crust thickens, and the atmosphere retains a composition recognizable in principle to modern observers. The planet's capacity to recover from cosmic violence establishes the pattern of resilience that will define its future. In the aftermath of so much destruction, a new kind of order emerges, a world no longer defined by molten chaos, but by cycles of weather, water, and rock interacting under the steady governance of gravity and heat. The scars of bombardment remain buried beneath younger layers, reminders of a time when survival itself was a process of continual renewal. The Earth has crossed a threshold. It is still young, but it now possesses the durability of a true planet. In the silence that follows the waning of bombardment, the Earth begins to show the first signs of enduring stability. Though its surface remains geologically active, portions of the crust now survive long enough to be altered rather than destroyed. These areas record the earliest geochemical memory of the planet, preserved not in large formations, but in microscopic minerals known as zircons. Zircon crystals, composed of zirconium silicate, are extraordinarily resistant to heat and chemical change. Once formed, they can survive melting, erosion, and metamorphism, carrying within their atomic structure the isotopic fingerprints of the environment in which they crystallized. The discovery of ancient zircons within much younger rocks provides humanity's only direct evidence of the Hadean surface. Their ages, measured at over 4 billion years, confirm that solid crust existed within a few 100 million years of Earth's formation. The chemistry of these tiny crystals reveals more oxygen. Isotopic ratios indicate that the rocks from which they crystallized interacted with liquid water at relatively low temperatures, suggesting that stable oceans and crustal regions coexisted even amid the planet's turbulent youth. The implication is profound. It means that despite the intensity of impacts, despite the internal heat and instability, pockets of crust cooled sufficiently to host liquid water and to endure long enough for zircons to form and survive. These were not continents as understood today, but localized regions of felsic composition rocks, enriched in silica and aluminum lighter than the dense basalt that covered most of the planet. Such materials could form when basaltic crust melted, partially producing lighter magma that rose and solidified near the surface. In this way, Earth began to differentiate chemically, not only by density but by mineral composition, setting the stage for the continental crust that would later dominate the planet. The survival of zircons through cycles of melting and burial implies that early crustal recycling was less absolute than once thought. Some fragments resisted complete reabsorption into the mantle, allowing them to persist across multiple geologic episodes. Around these stable nuclei, new rock accumulated, cooled, and recrystallized, creating protocontinental zones within the wider oceanic landscape. These early fragments likely floated above hotter, denser mantle domains, their buoyancy protecting them from immediate destruction. The presence of liquid water played a crucial role in their persistence. Water lowered the melting point of surrounding rock, promoting partial melting that allowed crustal regeneration without total obliteration. It also enhanced chemical weathering at the surface, altering minerals and facilitating the formation of sediments. These processes combined to stabilize the lithosphere, incrementally producing a patchwork of solid regions amid a dynamic environment. The geochemical clues preserved in zircons point to a surface temperature regime far cooler than the magma-dominated world that existed before. Instead of continuous molten fields, much of the planet may have resembled a volcanic archipelago surrounded by warm, mineral-rich seas. Rainfall and runoff acted upon these islands, creating chemical gradients between rock and water. In these gradients, elements such as silicon, aluminum, and oxygen cycled between solid and liquid forms, giving rise to complex mineral assemblages. The atmosphere above these evolving surfaces was still dense and carbon dioxide rich, but sunlight could now reach the ground more consistently. Clouds formed and dissipated in daily cycles, and the interplay of evaporation and precipitation became regular. The hydrosphere stabilized further, its temperature moderated by interactions with the solid crust below. In this more temperate environment, zircons crystallized within small bodies of granitic magma generated by localized melting. Some of these magmas formed deep within the crust and cooled slowly, allowing large, well-ordered crystals to develop. When later volcanic activity or erosion exposed these rocks, fragments entered sediments or were incorporated into new magmas, preserving their isotopic signatures through every transformation. Their ages and compositions reveal that the crust was already chemically diverse, containing both mafic and felsic components. This diversity indicates a planet that had progressed beyond its earliest homogeneous state into one capable of internal recycling and differentiation. Each zircon thus serves as a tiny archive of conditions, temperature, pressure, and the presence of water that define the early Earth. The isotopic evidence also suggests that weathering processes were active on land surfaces. Alteration of primary minerals by water leads to the formation of clays and oxides, which in turn influence the composition of sedimentary layers. Even in the absence of life, these chemical cycles began to shape the global environment. Carbon dioxide from the atmosphere dissolved into rainwater, forming weak acids that reacted with silicate minerals. This process drew carbon from the air and deposited it in solid form, providing one of the earliest mechanisms of climate regulation. Over geological timescales, such interactions would prevent runaway greenhouse conditions, keeping surface temperatures within the range that allowed water to remain liquid. The persistence of zircons across billions of years demonstrates not only their physical resilience, but also the continuity of Earth's crustal processes. Although the original Hadean rocks have long since been destroyed, the zircons they contained outlived them, surviving burial metamorphism and recycling into new rocks during later eons. Their continued existence provides a rare, tangible connection to an otherwise vanished world. From these microscopic crystals, scientists infer that the early Earth achieved thermal and chemical balance earlier than once believed. The planet was not an unbroken inferno until the Archean, but instead experienced intervals of calm, where crust, ocean and atmosphere interacted in sustained equilibrium. During these intervals, surface heat flow diminished enough to permit localized cooling, while convection in the mantle continued to transport energy outward. The result was a self-regulating system in which solid crust formed, melted and reformed without complete reset. The balance between creation and destruction produced the first geological cycle's precursors to the tectonic and sedimentary processes that would dominate later history. The evidence carried by zircons also implies that continents began as isolated patches rather than continuous landmasses. These early highlands would have protruded from shallow seas, altering atmospheric circulation and creating distinct weather patterns. Rainfall concentrated chemical weathering along their slopes, while erosion carried sediments into surrounding basins. In these marginal environments, the fundamental exchanges between rock, water and atmosphere became established. The Hadean Earth, once imagined as wholly molten and lifeless, thus reveals itself as a world of complexity and variation. The stability recorded in zircons is not global but regional and transient, yet it represents a decisive turning point. It shows that within a few 100 million years of formation, Earth possessed both solid crust and liquid water, coexisting under a dynamic atmosphere. The ingredients for a habitable planet, rock, air and ocean in balance were already present. Though far from the conditions that would later support life, the planet had achieved a degree of equilibrium. The Hadean landscape, still reshaped by impacts and volcanism, now held within it enduring records of stability. These records, encapsulated in crystals smaller than a grain of sand, testify that even in the most chaotic beginnings, moments of order emerged, and from that order the groundwork for all future geological and biological evolution was quietly laid. As the early crust stabilizes and fragments of continental material begin to endure, the interior of the planet continues its long decline in temperature. The heat accumulated during formation augmented by radioactive decay, and the energy of impact now dissipates into space through conduction, convection and radiation. The rate of heat loss governs nearly every process of the Hadean Earth: the motion of the mantle, the activity of volcanoes, the persistence of the atmosphere, and the renewal of the crust. Deep below the surface, the mantle remains largely molten, but convection currents carry heat outward through giant, slowly circulating plumes. Hot material rises toward the base of the crust, cools as it releases energy, and then sinks again toward the core. These convective loops operate on a planetary scale with cycles that last millions of years. They transport energy efficiently, preventing the planet from freezing too quickly and maintaining dynamic interactions between interior and surface. The behavior of this early mantle differs markedly from that of later eons. The viscosity of molten silicate under extreme heat is low, allowing motion that is vigorous and turbulent. Columns of hot rock rise rapidly while cooler material sinks, with equal force producing a churning environment beneath the solidifying crust. This movement drives volcanism at the surface, where cracks in the crust release lava and gas. Each eruption relieves internal pressure and alters the chemistry of the atmosphere. The global heat flux during this time is many times greater than in the modern world. The surface remains hot, but temperature gradients begin to form, marking a critical shift toward layered dynamics. The upper mantle, partially solidified, becomes sluggish compared to the still fluid regions below. This stratification introduces resistance to motion and begins to concentrate convection into discrete zones. These zones correspond to the earliest prototectonic cells, the ancestors of plate systems that will later shape the continents. Through them, heat escapes unevenly, creating alternating belts of uplift and subsidence on the surface. These differences manifest as volcanic ridges and basins where molten material pools. The circulation of heat through the mantle also drives chemical differentiation. As convection brings molten material to shallower depths, volatile elements escape, and lighter minerals crystallize while dense residues sink back downward. Over time, this repeated cycling sorts the mantle by composition, as well as temperature, producing layers with distinct mineral assemblages. The deepest regions near the core mantle boundary act as reservoirs for refractory elements and primordial heat. These zones remain partly molten for hundreds of millions of years, feeding plumes that rise intermittently to the surface. The outer layers gradually cool, forming a more rigid shell that insulates the interior and slows overall heat loss. Despite this, insulation cooling continues because radiation to space remains efficient. The atmosphere, though thick, no longer consists of opaque silicate vapor, and thermal energy escapes through infrared emission. This balance allows the Earth to maintain a temperature suitable for the persistence of oceans without reverting to global freezing or remelting. The rate of cooling determines the rhythm of geological change. When heat flow increases locally, crustal melting and volcanism intensify. When it decreases, crust thickens and stability returns. These fluctuations occur globally, but asynchronously, creating a patchwork of active and quiescent regions. The surface evolves from a chaotic sea of lava to a planet of shifting volcanic provinces separated by cooler plateaus. Overlying all of this is the planet's growing capacity to regulate its own energy output. As the mantle's convective vigor diminishes, the thickness of the crust increases, forming an effective thermal boundary that controls the escape of heat. Conductive cooling through the crust becomes the dominant mechanism at smaller scales, while large-scale convection continues to drive deeper circulation. The result is a planet that cools from the outside inward, its surface increasingly stable, even as its interior remains dynamic. The chemical exchanges between the mantle and crust are intensified by this process. Magma generated at depth rises and interacts with overlying rocks, altering both compositions. Elements such as potassium, sodium, and aluminum concentrate near the surface, while iron and magnesium dominate the lower mantle. This redistribution sets the geochemical architecture of the Earth, influencing how minerals crystallize and how future tectonic plates will behave. The heat flow also determines the activity of the magnetic field. In the core, composed primarily of molten iron and nickel, convection persists due to residual heat and the gradual crystallization of metallic material. This movement generates an early dynamo, producing a magnetic field that fluctuates in strength and direction. Though weaker than the modern field, it provides partial shielding against solar radiation, helping the atmosphere endure through periods of strong solar wind. The combination of internal cooling and magnetic protection allows the planet's volatile inventory to remain largely intact. The exchange of gases between interior and atmosphere continues, but the loss to space diminishes. As a result, pressure and temperature at the surface become more stable. Oceans deepen, the crust thickens, and volcanic outgassing declines to a steady rate. The balance between internal heat release and external radiation stabilizes the planet's climate within a narrow range defined by the properties of water and rock. Even so, the mantle remains far hotter than it will ever be again. Its convective power maintains a level of tectonic mobility unseen in later ages. Entire regions of crust may founder and sink into the depths, recycling material and carrying surface chemistry into the interior. This recycling contributes to the continued evolution of the mantle's composition. The isotopic signatures of later rocks reveal traces of these early exchanges, evidence that crustal materials were already being reprocessed within a few 100 million years of formation. The cooling of the mantle also influences the rate of rotation. As internal energy dissipates, mass redistributes, and the Earth's moment of inertia changes slightly, slowing its spin. The day lengthens fractionally with each passing epoch, and tidal friction from the Moon accelerates this trend. The combined effects of mantle cooling and tidal forces gradually reduce both rotational speed and internal turbulence. The Earth grows quieter, more measured in its motions. The energy that once erupted violently through global magma oceans now moves through channels of controlled convection and localized volcanism. The surface, though still restless, can support structures that last for geological spans of time. Mountains formed by volcanic accumulation rise and erode rather than vanish in molten floods. Basins persist long enough to hold oceans that circulate and exchange heat with the atmosphere. The feedback between mantle dynamics and surface processes creates a system approaching equilibrium. Heat flow, once the cause of constant upheaval, becomes the heartbeat of a planet entering maturity. By the end of the Hadean, this gradual cooling will define the transition into the Archean world, a planet where crust, ocean and mantle exist in steady interaction. The relentless flow of energy from core to surface continues, but it is now tempered, directed and rhythmic. The Earth's fiery youth gives way to endurance, its once blinding glow, dimming into the steady warmth of a living planet that has learned how to sustain itself across cosmic time. As the mantle cools and the crust thickens, the mode of planetary motion begins to change. The Earth is no longer dominated by vast molten seas, but by solid plates of rock floating upon a convecting interior. Yet these plates are not the rigid drifting continents of the modern world. In the Hadean Eon, tectonic behavior is experimental shifting between modes as the planet searches for equilibrium. The enormous heat still trapped within the mantle drives powerful convection, but the overlying crust, though solid, remains weak and thin. Instead of sliding as organized plates, large sections of crust may break apart or overturn wholesale. The term stagnant lid is used by modern scientists to describe this early state, a regime where the surface remains mostly intact, while convection churns beneath, punctuated by catastrophic episodes of melting and renewal. The earliest tectonic style likely alternates between such stability and global resurfacing events, triggered by the accumulation of internal heat. When temperature and pressure below the crust reach a threshold, upwelling plumes pierce the surface, flooding entire regions with lava and recycling old material into the mantle. The result is a planet that cools in pulses rather than continuously, with long, quiet intervals punctuated by massive volcanic renewal. The pattern leaves behind a surface mottled with contrasting terrains, some ancient and weathered, others newly formed and glassy. In this dynamic environment, the first proto-continents may have begun as buoyant rafts of lighter, silica-rich rock produced by partial melting of the basaltic crust. These rafts, less dense than surrounding material, resist submersion and act as insulators over the mantle. Around their margins, molten basalt wells upward, forming ridges where new crust is added. Between them, denser material sinks, dragging fragments of the surface downward into the deeper mantle. This cycle resembles modern subduction in principle, but lacks the precise boundaries and organized motion of later tectonic plates. It is a world governed by thermal gradients rather than mechanical divisions. Over time, as the interior continues to cool, these processes slow. The stagnant lid becomes thicker and more resistant to rupture. The frequency of global overturns decreases, and localized zones of deformation become the primary outlets for internal energy. In these zones, partial melting produces magma that rises through fractures, feeding volcanoes and creating small basins of new crust. The interplay between extension and compression, stretching where heat escapes folding, where cooling contracts, marks the first recognizable tectonic activity. These forces are immense, shaping the early landscape into highlands, basins, and rifts. Some of these features persist long enough to influence the flow of water and the formation of sediments. The interaction between tectonics and the hydrosphere intensifies chemical cycling. Rainwater infiltrates cracks and reacts with hot rock, altering minerals and weakening the crust. The infiltration of water into deeper zones lowers the melting point of the mantle, promoting further volcanism and feeding a continuous feedback loop. In this way, surface processes begin to influence internal dynamics for the first time. The Earth's cooling becomes a coordinated system where atmosphere, hydrosphere, and lithosphere exchange energy and material. Although true plate tectonics will not develop until the Archean Eon, the mechanical groundwork is already visible in the Hadean. The presence of compositional layering, thermal convection, and buoyant crustal fragments makes the future mode of planetary motion inevitable. For now, however, the process remains inefficient. Frictional forces between solid crust and viscous mantle are high, and the lack of rigid plates prevents sustained lateral movement. Instead, deformation occurs vertically, as crust founders and resurfaces repeatedly. The intervals between these resurfacing events lengthen as heat flow declines, allowing longer periods of crustal preservation. During these quieter times, erosion by wind, rain, and waves reshapes the surface, depositing sediments in low-lying areas. These sediments, later buried and heated, form the first metamorphic rocks recording conditions of pressure and temperature within the early crust. Their presence indicates that mountain building and burial processes, however rudimentary, were already at work. Meanwhile, deep within the mantle, convection patterns evolve from chaotic plumes to more stable cells. The scale of these cells determines the spacing of volcanic centers at the surface. Each plume brings material from near the core mantle boundary, enriched in elements that alter the chemistry of the crust. This recycling establishes a long-term geochemical connection between deep Earth and the surface, linking the evolution of the planet's interior to its exterior expression. The continuous interplay between melting and crystallization creates zones of varying density and rigidity, further diversifying tectonic behavior. The early crust becomes a patchwork of domains, each responding differently to thermal stress. Some regions rise to form plateaus, others sink to form basins filled with hot, dense rock. The boundaries between them become zones of weakness where deformation concentrates. Over geological time, these zones will evolve into the suture lines and fault systems that characterize mature tectonic plates. For now, they serve as conduits for magma and heat releasing pressure from below, and sustaining a delicate balance between creation and destruction. The global pattern of heat flow begins to reflect this structural organization. Volcanic outgassing diminishes as the mantle cools and the atmosphere grows more stable. The reduction in surface temperature allows oceans to deepen and persist for longer intervals, further stabilizing the climate. Water acts as a lubricant for tectonic processes, promoting sliding and partial melting in regions of stress. With each cycle of deformation, the crust grows more complex, incorporating materials of different ages and compositions. This complexity marks a critical milestone in planetary evolution. The Earth is no longer a uniform sphere but a differentiated system where energy moves through interconnected pathways. The magnetic field maintained by convection in the liquid core interacts with the mantle's motion to influence the distribution of heat. Variations in field strength may even affect volcanic patterns by altering the behavior of charged particles in the atmosphere, though such interactions remain poorly understood. What is clear is that the planet has entered a new phase of dynamic balance. The earliest tectonic styles represent a transition from chaos to organization. They convert the raw thermal energy of formation into mechanical work shaping the surface and regulating the planet's cooling. Though the process is slow and often catastrophic, it transforms the Earth from a molten sphere into a structured world with a living surface. By the close of the Hadean, the crust is thick enough to resist global melting, yet thin enough to remain flexible under stress. Volcanic arcs and rift zones crisscross the landscape, linking the interior to the atmosphere through cycles of degassing and condensation. The foundations of geology are in place: convection, volcanism, erosion, and recycling. The Earth's surface, once transient and featureless, now exhibits enduring form. Mountains rise and erode, basins fill and empty, and the rhythmic breathing of the planet begins. This emergence of structure marks the threshold between the chaotic birth of a planet and the ordered evolution of a world capable of sustaining complexity. With a solid crust established and the hydrosphere in full presence, the interaction between rock and water becomes one of the dominant forces shaping the Hadean Earth. Rain falls steadily across vast volcanic plains, collecting in shallow basins and flowing through channels carved by erosion. The surface, once molten and barren, now undergoes chemical transformation at every contact between liquid and mineral. When rainwater reaches newly solidified basalt, it reacts immediately, dissolving ions of calcium, magnesium, sodium, and potassium from the rock. These ions are carried into lakes and oceans, altering the chemistry of the early seas. The process of weathering begins slow but relentless, a fundamental mechanism by which the atmosphere, hydrosphere, and lithosphere exchange material. The water itself is acidic, containing dissolved carbon dioxide and volcanic gases such as sulfur dioxide and hydrogen chloride. These acids accelerate mineral dissolution, turning solid rock into clay-like residues. As runoff flows downhill, it accumulates sediments of altered minerals that settle into low-lying basins. Each cycle of rainfall and evaporation concentrates dissolved elements, making the primitive oceans increasingly saline. The early chemistry of seawater is dictated by this continuous weathering, a balance between input from erosion and removal through mineral precipitation. Over time, as volcanic gases wane and atmospheric composition stabilizes, rainfall becomes less corrosive, allowing the surface to retain more solid rock. Yet the chemical exchange never ceases. Basalts exposed along shorelines react with seawater in hydrothermal systems, where heat from below circulates water through cracks and fissures. These hydrothermal vents act as powerful chemical reactors, leaching metals such as iron, manganese and nickel from the crust and depositing them again as minerals along vent walls. The process not only alters the crust composition, but also regulates ocean chemistry, balancing concentrations of key elements. Water penetrates deep into the crust where it interacts with hot rock and newly formed magma. This interaction forms serpentine and other hydrated minerals, incorporating water into the crystalline structure of the lithosphere. In doing so, the planet begins to store part of its surface water internally. The cycling of water between crust and mantle becomes established, marking the beginning of Earth's long-term hydrological regulation. Each volcanic eruption returns some of that water to the surface, while subduction-like processes, still primitive, carry hydrated minerals downward. This circulation links surface and interior in a dynamic exchange that moderates both temperature and chemistry. Weathering also plays a key role in drawing down atmospheric carbon dioxide. Rainwater absorbs the gas from the air and combines it with dissolved rock ions to form carbonates. These compounds precipitate as solid minerals, locking carbon into the crust. Over time, this process counterbalances volcanic emissions, stabilizing the greenhouse effect and maintaining temperatures suitable for liquid water. Though the scale of equilibrium remains unstable during the Hadean, the mechanism itself is already active. The atmosphere's composition becomes self-regulating through feedback between weathering and degassing a system that will persist for billions of years. On the surface, the landscape is continually reshaped by these interactions. Erosion removes the peaks of volcanic mountains while sedimentation fills the basins below. River-like systems driven by gravity and rain cut channels through soft rock, transporting clay and sand toward the seas. Impact craters left from earlier bombardments become natural reservoirs where water collects and sediments accumulate. Within these basins, layers of fine material settle over time, forming the earliest sedimentary deposits. Although later tectonic activity will destroy nearly all trace of them, their brief existence signals the emergence of a stable hydrological cycle. The constant movement of water across rock also affects the planet's energy balance. Evaporation absorbs heat from the surface, transporting it into the atmosphere where condensation releases it again. This exchange moderates temperature differences between equator and pole, creating a primitive climate system. Winds arise from these gradients, moving moist air across continents and spreading weathering effects globally. The young Earth's climate, though still warm, begins to exhibit regular patterns of circulation. In the deep oceans, hydrothermal activity generates chemical gradients that persist for millennia. Fluids rich in metals and gases rise from vents mixing with cooler seawater to form plumes that spread across the ocean floor. These gradients create zones of intense mineral precipitation, producing layered deposits of sulfides and oxides. Such regions represent the planet's first geochemical ecosystems networks of reaction, rather than biology but foundational nonetheless. In these environments, energy flows continuously from the interior to the surface through water-rock interaction. The crust itself evolves as weathering and alteration proceed. Basalt, once dominant, gives way to more complex assemblages of minerals. Hydrated rocks such as serpentinite and chlorite-bearing schists begin to form in regions of prolonged hydrothermal circulation. Their lower density and higher water content alter the buoyancy of the crust, encouraging further differentiation between oceanic and protocontinental domains. Over millions of years, this differentiation amplifies tectonic contrasts, setting the stage for later plate behavior. As water continues to interact with rock, it infiltrates deeper, carrying dissolved elements into the mantle. The feedback between surface processes and internal convection strengthens. Regions of subcrustal hydration lower the melting point of adjacent rock, leading to localized volcanism that releases new gases and heat. This exchange maintains a steady flow of material between the planet's layers, preventing stagnation. The atmosphere remains thick and warm but begins to clear slightly as volcanic emissions decline. Sunlight filters through clouds, casting diffuse illumination over seas and islands. The color of the ocean changes from dark grey to greenish blue as mineral concentrations shift and the sky grows paler. The surface of the Earth now reflects both the light of the sun and the glow of its own heat. The balance between internal and external energy defines its climate and chemistry. Through the interaction of water and rock, the crust becomes a living interface, reactive, renewing, and capable of preserving history within its minerals. Even without life, the planet functions as a system of continual transformation. Each raindrop contributes to the long-term moderation of the atmosphere. Each volcanic eruption replenishes the material removed by weathering. Together, these processes drive the evolution of the Earth toward greater stability. By the end of the Hadean, the surface has become a mosaic of landscapes, volcanic plateaus, weathered plains, shallow seas, and ancient highlands. The chemistry of the oceans has stabilized around a composition that will endure, dominated by salts derived from basaltic alteration. The air, once dense and opaque, has thinned enough to reveal a faint blue hue. The interaction between water and rock has altered every component of the planet, linking atmosphere, hydrosphere, and lithosphere into a single self-regulating whole. This equilibrium, achieved through countless cycles of erosion, precipitation, and metamorphism, defines the final transformation of the Hadean world. The stage is now set for the possibility of habitability, not yet for life itself, but for the steady environment that will one day make it possible. By the closing chapters of the Hadean Eon, the Earth has evolved into a planet of balance. The atmosphere, hydrosphere, and crust function together in cycles that maintain moderate conditions on the surface. The thick veil of carbon dioxide and steam that once trapped unbearable heat has thinned, replaced by a dense but stable blanket of nitrogen water vapor and residual greenhouse gases. Temperatures, while still higher than in later ages, are now within the narrow range that allows liquid water to persist across most of the planet. Oceans occupy vast basins circulating heat and minerals through global currents driven by both wind and geothermal energy. The crust, though thin compared to modern standards, endures long enough for weathering and sedimentation to sculpt permanent features. The mantle below continues to convect, releasing energy that sustains volcanic activity, but no longer at a level that resets the surface entirely. In this moderated state, the Earth approaches a delicate threshold, the emergence of a stable, habitable world. The conditions that define habitability are physical rather than biological. At this stage, temperature, pressure, and the availability of water and energy. Each of these variables now lies within a range that allows complex chemistry to occur. The oceans, rich with dissolved minerals leached from volcanic rock, provide a vast medium for chemical reactions. Silica, iron, magnesium, and trace elements circulate through hydrothermal vents and surface currents. Electrical storms driven by the still active atmosphere ignite countless reactions among gases and aerosols, producing transient compounds of carbon and nitrogen. Ultraviolet light from the young sun, though intense, is filtered by clouds and possibly by traces of photochemical haze produced by volcanic emissions. This interplay of radiation and chemistry creates an environment of dynamic equilibrium, energetic, but not destructive, stable, yet full of change. The energy gradients that once tore the planet apart now sustain slow, continuous processes. Heat from the mantle escapes through volcanic vents mixing with cold seawater to produce localized regions of strong chemical disequilibrium. Here, water rich in carbon dioxide and metal ions meets reducing gases such as hydrogen and methane, creating conditions suitable for complex reactions. These gradients, powered by geothermal heat, represent potential sources of chemical organization that will later be critical for life. For now, they mark the transition from a purely physical planet to one where chemistry begins to explore new forms of complexity. The hydrosphere no longer transient acts as both solvent and stabilizer. It moderates temperature fluctuations and distributes heat globally. Atmospheric circulation and ocean currents transport moisture and energy, forming primitive weather systems. Rain and evaporation maintain the water cycle, which in turn controls erosion, sedimentation, and chemical exchange between surface and interior. The presence of stable oceans allows the slow concentration of solutes. As rivers carry ions from weathered rock into the sea, the chemistry of the water evolves toward equilibrium. Salts accumulate while volcanic emissions maintain acidity that prevents stagnation. This delicate balance between input and removal defines the planet's chemical environment. The first crustal platforms, buoyant and silica-rich, rise above sea level as protocontinents breaking the monotony of global ocean. Their surfaces, weathered by rainfall and wind, feed sediments into surrounding basins. These highlands alter atmospheric patterns, creating regional differences in rainfall and temperature. They also provide a steady source of minerals that enrich the oceans. The interaction between land and sea further amplifies stability, distributing mass and regulating the planet's heat budget. The role of the moon becomes increasingly significant during this time. Its gravitational pull maintains strong tides that circulate ocean water across basins, preventing stagnation and enhancing mixing. Tidal friction gradually slows Earth's rotation, lengthening the day and moderating climate extremes. The axial tilt stabilized by the moon's presence prevents chaotic changes in sunlight distribution, ensuring that temperature variations remain within habitable bounds. These subtle effects, the result of celestial mechanics, contribute to the steady rhythm of the Hadean Earth's maturing climate. As the bombardment of large asteroids fades into history, the planet's surface becomes calmer. Meteors still fall, adding trace amounts of organic material synthesized in the cold reaches of space, but none are large enough to sterilize the planet. The combination of gentle impacts and active internal chemistry introduces new compounds into the atmosphere and ocean, enriching the prebiotic environment. The Earth, once defined by fire and catastrophe, now supports the quiet interplay of rock, water, and gas. Within hydrothermal systems, water percolating through fractured basalt absorbs heat and reacts with minerals, producing alkaline fluids that mix with the slightly acidic ocean. These interactions create natural electrochemical gradients and mineral surfaces capable of catalyzing further reactions. The constant exchange between ocean and crust generates chemical diversity and potential pathways for molecular complexity. Even without life, the planet exhibits self-sustaining cycles that mimic metabolism in their feedback and stability. The emergence of such conditions marks the boundary between geology and habitability. The key factor underlying this transition is balance. Volcanism provides gases that maintain atmospheric pressure and supply nutrients. Weathering removes carbon dioxide and moderates temperature. Oceans distribute heat and buffer chemical changes. Each system regulates the others through feedback loops that prevent runaway extremes. The surface temperature remains warm enough for liquid water but cool enough to avoid sterilizing heat. Carbon dioxide levels, though, still high support a greenhouse effect that offsets the faint young sun's reduced luminosity. This balance between energy input and radiative loss maintains a planetary equilibrium that endures for millions of years. The Hadean world for the first time achieves environmental stability on a global scale. Beneath the oceans, the crust continues to evolve. Partial melting and metamorphism create a chemically diverse lithosphere. Elements such as sulfur and phosphorus, vital to later biological processes, circulate between mantle and ocean. Their presence in hydrothermal systems, combined with the continuous supply of energy, ensures that the conditions necessary for organic synthesis are widespread. While life has not yet appeared, the planet is now physically and chemically ready for it. The transition toward habitability is not marked by any single event, but by the accumulation of equilibria, each process finding its steady state, each feedback reinforcing stability. From this equilibrium arises a planet unlike any other in the solar system, one that maintains liquid water, moderates its own temperature, and supports a complex chemistry capable of sustaining future evolution. The Earth's long struggle between fire and water impact and renewal has produced a world both resilient and fertile. By the end of the Hadean Eon, the surface no longer glows with molten light but reflects the muted blue of oceans beneath a pale sky. Volcanic islands rise through mist surrounded by steaming seas, their slopes darkened by mineral deposits. Rain falls gently over landscapes once ruled by flame. The energy that once tore the planet apart now sustains its harmony. The Earth has entered a state of calm complexity, the quiet threshold where the physics of formation gives way to the potential for life. The close of the Hadean Eon marks a profound turning point in the planet's history. After hundreds of millions of years defined by impact, melting, and renewal, the Earth enters a quieter phase of evolution. The violence of formation subsides into the measured rhythm of geological time. The mantle's convection slows, the crust thickens, and the hydrosphere stabilizes into a permanent system of oceans, atmosphere, and weather. The processes that began as chaotic exchanges of heat and matter now operate within feedback loops that maintain long-term equilibrium. This transformation defines the transition to the Archean Eon, when Earth becomes fully recognizable as a living planet of rock, water, and air. The physical structure of the planet is now established. A dense metallic core spins at the center, generating a magnetic field that shields the atmosphere from the solar wind. Above it, the mantle convects in organized patterns, transferring heat outward through slow, steady motion. The crust, though still thinner and more dynamic than in later ages, now endures across continents of limited size. These early continental nuclei, composed of granitic material, formed by partial melting of basalt, stand as lighter, buoyant masses surrounded by denser oceanic crust. Around their margins, volcanic arcs and rift zones mark boundaries of tectonic motion. These zones are the first prototypes of subduction and spreading, where material is continuously created and destroyed. In this new tectonic framework, the Earth begins to recycle itself not through global overturn, but through local persistent processes. The atmosphere, once dominated by carbon dioxide and steam, has evolved into a mixture more stable and transparent. Water vapor condenses, regularly forming clouds that regulate the climate. Nitrogen has become the main component of the air, a passive but vital gas that cushions temperature and supports long-term chemical balance. Trace amounts of carbon dioxide and methane maintain the greenhouse effect, preventing the planet from freezing under the faint young sun. The sky, now clear in many regions, reveals a pale blue color during the day and a dark, star-filled canopy at night. Lightning continues to flash through storms, discharging energy into a moist, reactive atmosphere. Each bolt of lightning drives further chemical reactions among carbon, nitrogen, and hydrogen gases, producing molecules that drift into the oceans and dissolve. The hydrosphere, vast and deep, covers most of the surface, its circulation governed by tides, winds, and geothermal heat. Waves erode the edges of volcanic islands, grinding rock into sand that settles into basins. Rivers form across highlands, carrying minerals into the sea. This constant exchange between land and water redistributes heat and nutrients, building sediments that will become the foundation of the sedimentary rock record. Beneath the oceans, hydrothermal vents release streams of mineral-rich water sustaining chemical gradients that span the entire ocean floor. These vents mark the continuation of a process that began in the Hadean, the constant interaction between the planet's interior and its surface. Through these systems, heat escapes, minerals circulate, and chemical energy flows outward. The early crust near these vents shows signs of alteration by seawater, forming minerals that trap water and trace elements. These reactions link the hydrosphere to the lithosphere in cycles of continuous exchange. The presence of such systems indicates that the planet's internal heat, though reduced, still drives vigorous activity. The Archean Earth will inherit this dynamic foundation and refine it into the steady engine of plate tectonics. The climate of the late Hadean is warm but stable. The oceans remain liquid, the atmosphere thick enough to retain heat, but no longer stifling. Clouds moderate solar radiation, producing global temperatures that support the persistence of liquid water even at high latitudes. The faintness of the young sun is offset by greenhouse gases, a balance maintained by volcanic degassing and chemical weathering. Whenever atmospheric carbon dioxide rises, rain and rock interact to draw it down. When it falls, reduced weathering allows it to rebuild. This equilibrium keeps the surface temperature within the limits of habitability. The system is already self-correcting, a geochemical thermostat that will sustain the planet for billions of years. The crust's growing complexity contributes to this stability. Areas of lighter rock rise above the oceans, forming the first long-lived continental platforms. These granitic masses, enriched in silica and aluminum, resist submersion and erosion better than basalt. Their emergence marks the dawn of true continents, even if small and scattered. Around them, chains of volcanic islands form where magma wells upward, while deep basins collect sediments washed from highlands. These contrasts in elevation establish enduring patterns of circulation in both atmosphere and ocean. Winds follow temperature gradients between land and sea, while currents move heat toward the poles. The planet's internal and external systems thus converge into harmony, each influencing the other through cycles of energy and matter. The magnetic field, strengthened as the core continues to differentiate, now envelops the planet in a stable magnetosphere. This invisible shield deflects solar particles and reduces atmospheric loss, preserving the gases essential for climate regulation. At the same time, the Moon's gravitational pull continues to govern tides and the rotation rate of the planet. The day lengthens slowly as angular momentum transfers outward. Longer days allow more even distribution of solar heating and promote the development of a regular climate rhythm. The Earth's spin, once frantic and unstable, now settles into the rotation of a mature world. With these systems in place, the conditions for habitability are fully realized. The planet's surface supports persistent oceans, continents, and an atmosphere capable of recycling its components. The energy balance between Sun, Earth, and space maintains moderate warmth, while internal heat drives geological renewal. Chemical complexity abounds in both ocean and crust, producing gradients of temperature, pressure, and composition that sustain reactions across scales. The Earth has become not merely stable, but dynamic a planet in which stability and change coexist in equilibrium. The Hadean's end does not arrive abruptly. It fades gradually into the Archean as impacts cease, and the last large craters fill with sediment and lava. The boundaries between eons are drawn by transformation, not catastrophe. What began as a molten sphere under constant bombardment has become a world of oceans and skies of heat, flowing quietly beneath solid ground. The architecture of the modern Earth is already visible in outline: a layered interior circulating mantle, active crust and self-regulating climate. From this structure will emerge the processes that define the next 2 billion years: plate tectonics, continental drift, and eventually the rise of life. The Earth at the dawn of the Archean stands as both survivor and origin. Its crust bears the scars of every prior epoch, its mantle retains the memory of ancient heat, and its oceans carry the chemistry of endless reaction. The violent creation of the Hadean has given way to the calm persistence of geology. The planet that once glowed with molten brilliance now shines through reflection. Its surface cooled, its systems balanced. The next age will not erase the Hadean's legacy, but build upon it as the stable rhythms of rock, water and atmosphere set the stage for biology's first appearance. The world is ready. The silence that follows 400 million years of fire is the sound of a planet becoming alive,